tout le monde. Hello, everyone. So today we're excited to have Clarke Smith from École Normale Supérieure, INRIA, to talk about his recent work there on magnifying quantum phase fluctuations with Cooper preparing. So Clarke did his PhD in the group of Michel Devoré from, I guess, 2013 or 12 to, am I right?
Yeah, that's when I started, and then I finally finished 2018.
Okay, 2018, and then you joined the group of Zaki as a postdoc in Paris. So, Clarke, the floor is yours.
Thanks a lot. Thanks a lot, Joachim, for inviting me. I'm pretty excited to talk about this experiment that we've done over the last year in Paris, which is really aimed at actually seeing how much we can build, or what kind of circuit we can build that has a ground state that is delocalized. And as I'll try to convince you, this is very intimately related to the notion of magnifying or increasing the effective amplitude of quantum fluctuations of the superconducting phase. Okay, so for everyone who works in circuits, which I guess is all of you, we basically are armed with three main elements. We have this Josephson junction, which is this crossed box, and it's a nonlinear inductance in parallel with a capacitor. And in addition to that, we also have linear inductors and linear capacitors. So once you read Michel's Les Just notes from 1997, you see that mathematically we can solve just about any circuit that's arranged in any geometry. This is a particularly complicated one. And we're tempted to think that we can simulate a huge class or almost any class of Hamiltonians with such devices. But is this an illusion, or is this really what happens? So if you go about doing circuit quantization, what you find is that there are different degrees of freedom, which correspond to different electromagnetic modes, and that each of these modes, the self-dynamics of which can be depicted using the simpler circuit on the right, which is a linear inductor, Josephson junction, and capacitor. And in general, we have a collection of these modes with interactions. So this particular circuit on the left, which is actually a 0 pi qubit with some extra elements, has 5 modes, and the interactions are quite extreme, and the interactions are very interesting. They can give rise to all the sorts of condensed matter phenomena and so on. But I'm not going to talk about them here. Actually, our interest in this experiment is just to ask or sort of try to answer the question of what physics remains to be explored with just this single mode or single degree of freedom circuit. Okay, so if we look a little bit more in depth, we are inclined to introduce characteristic energy scales for the three elements here. There's a EL corresponding to the inductive energy of the linear inductor, and EJ corresponding to the Cooper pair tunneling energy across the junction, and EC, which is corresponding to the capacitive energy or charging energy of the capacitor. And since there's an inductive loop here threaded by the linear inductor and the Josephson junction, there can also be an external magnetic flux threading that loop. So here I've written it in units of the superconducting phase, which is phi. And this is just the difference in the BCS wave function phases on the top and bottom electrodes here. So the Hamiltonian has 3 terms, one corresponding to each of the 3 elements. There's a linear kinetic energy sort of term if you were talking in the phase basis. And then you have also a linear or a quadratic rather harmonic potential and a cosinusoidal corrugation on top. And here you see that the external flux plays the role of a phase or equilibrium offset between the Josephson term and the quadratic term. So there are 3 energy scales that determine the physics, and the overall energy shouldn't matter. So in the end, there's just 2 parameters that determine the relevant qualitative differences in the physics. So we're free to choose, for instance, EJ over EC and EL over EC as the 2 parameters, and to imagine a sort of phase diagram or a Mendeleev table. Here, you should note that crucially, the horizontal axis is broken towards the origin, where you can physically take the limit that EL goes to 0, in which case that's just to say that this inductor is very large. So you could easily patent make a circuit where this is not included. Here I'm also plotting, or here this is a plot stolen from this paper, which just came out in September in Nature from Vlad Manucharian's group in Maryland. And here they are also plotting in gray curves the probability that the phase is extending beyond a certain threshold. Here it's pi. So as you get closer and closer to the origin, the phase tends to extend. So if we look at these different types of circuits, of course, there are many other ones that have been invented, the RF squid, the phase qubit, the flux qubit, and so on. But here they've made a real effort to find the sort of prototypical qubits, the ones where the physics is actually qualitatively different between the different points. So the one that probably everyone's most familiar with is the transmon, where actually, since EL is 0, the Hamiltonian is strictly periodic in phi, and so it's a compact variable. And here I'm plotting the probability densities for the grounded and first excited state wave functions, which you see are nicely localized within this single potential well. It's of course on a ring, so you can imagine it being extending and being periodic. And then if we change this parameter EJ over EC, we're just changing the number of energy levels within that well. So for the transmon, there's this ratio is near 100, and there's something like 7 energy levels within the well. But the charge qubit, which came a little earlier, only had at most 1 level within the well. If we add an inductive shunt, as in the case of the fluxonium, what we have is, first of all, a non-compact phase, so it can extend far beyond minus pi to pi. And we see the appearance of multiple potential wells. So here you can see that there's sort of a small one, and then there's a main potential well, and there would have been another one depending on this particular value of the external flux. But regardless, despite having multiple potential wells, the parameter regime is such that these ground and first excited state wave functions tend to live within the lowest well. So the question they asked in this paper, and also what I'm asking in this talk, is this all? Is this all the physics that can really be seen with this circuit? And the answer is apparently not. In this paper, they invented something called the blochnium, which is actually just a fluxonium qubit, but in a very different limit, where the EL over EC ratio, which is roughly scaling as the inverse of the amplitude of quantum fluctuations of the phase, has gone down by at least an order of magnitude. And when that happens, then you see all these potential wells actually have come down so far that the ground and first excited state actually delocalize and can live within multiple potential wells at the same time. So in such a situation, mathematically, you can also describe this sort of circuit in terms of a quasi-charge representation. But in our particular work, we've taken a slightly different perspective, and we're talking mostly about ground state delocalization. So you may reasonably ask, why has this remain out of reach? Is it even worth doing? So naively, I'll just try to explain why it's difficult. If we try to make this was the x-axis in the previous plot, and if we're interested in making this very small so that the ground state is delocalized, we can write it in terms of the characteristic impedance of the circuit, which is the square root of the linear inductance over the capacitors, and also a fundamental constant of nature, which is the resistance quantum, which is in terms of Planck's constant, the electron charge. And what happens when you try to make, a large impedance circuit, in order to make this EL over EC ratio small, especially when you're using geometric structures like geometric inductances and capacitors, you find that this impedance tends to be very nearly on the order of the vacuum impedance, which is about 400 ohms. On the other hand, the resistance quantum is about 6.5 kilo ohms, and this is quite a big difference. So basically, you are tempted to think that the only way to increase this characteristic impedance over the resistance quantum is to use a non-geometric structure like a kinetic inductance or something. And just to sort of emphasize that why are basically there are two sort of characteristic impedance scales in nature, it's basically due to the fine structure constant, or equivalently the sort of natural scale for phase fluctuations versus charge fluctuations. So in this paper, they actually, I mean, it was a tremendous feat. What they did is they were able to decrease this ratio EL/C to about a factor of 100, which is, an order of magnitude or two bigger than what's been done before, or about just 1 order of magnitude. And what they did here is actually they've made a sort of standard fluxonium device, which is a junction, Dosen junction here. It's labeled 1, shunted by a large array of larger junctions. Here it's done on the Dolan bridge technique. And what they've done is they've actually under-etched the silicon underneath the junctions to the point where this entire superconducting loop has peeled off the substrate. So you can see these beautiful SEM images of the peeling. And this is pretty cool because basically all the different interstitial capacitances between all the various islands of this loop are going to have a much smaller the capacitance when it's suspended than when it's pinned. And that's just because the dielectric permittivity of vacuum is much smaller than that of silicon. So all the capacitance go down by the same factor. And when they get this enhancement reduction in terms of capacitance, what it means is they can add 5 or 10 times more Josephson junctions in that chain while keeping all the parasitic modes at high frequencies, and basically then correspondingly reduce their EL, which is to say increase their inductance. So it's not necessarily a free lunch. I think it remains to be explored exactly how reproducible these things are. I think one outstanding question is actually about how well all of these different islands in the circuit thermalize, especially when they're not anchored to the substrate. And then a sort of more practical matter is, in this particular experiment, they used a magnetic field from a solenoid type coil. But if you're imagining, more complicated circuits with multiple flux loops or multiple qubits on the same chip, it's a little bit less compatible with, say, an on-chip flux line type geometry. But nonetheless, this is a tremendous feat. This is and this sort of work and some of the discussions leading up to it inspired us to ask ourselves, can we do the same thing, but without spending a year in the clean room trying to optimize a particular fabrication recipe? Can we do it in another way, or is there even another way to do it? So in our what we sort of came up with was to, instead of thinking, so this is again a fluxonium type circuit where we have a Josephson junction here, it's got some extra lines and it's shunted by an inductor. And we sort of thought that instead of trying to increase the linear inductance by an order of magnitude, could we change something about the actual Josephson junction? So here we started to think about whether or not we could just imagine a Josephson junction or a generalized Josephson element with another additional parameter instead of just EJ and EC being mu, which is it could be an integer, 1, 2, 3, and 4, and then this will basically specify the period of the Josephson potential. So here we've just placed sort of haphazardly a mu right in the cosine, the usual cosine phi of the Josephson junction, and correspondingly we've decreased the charging energy by the same factor. This is to sort of preserve the general conjugacy between mu phi and n. So to see what this is doing, right now it's just a mathematical construct, but if we just look at conjugacy between charge and phase, we see that in the charge basis, this cosine mu phi should actually look like a sum of tunneling terms between n Cooper pairs across the junction or the element and n plus mu. So what it really corresponds to is mu multiples of Cooper pairs tunneling across this element. And to see why this would be sort of interesting, it's a bit natural. It's a bit natural to think about if mu is appearing in the cosine, to think that the amplitude of phase fluctuations might be bigger. But to sort of see this a bit more concretely, we can plot here a sort of standard Blochnium type potential and a ground state wave function for the case mu equals 1 and the same exact parameters, but just incrementing mu to 2. And we see that what happens is that the envelope of this ground state wave function has stayed basically the same between the two. See, the x scale has changed, but the number of actual wells has been doubled. So it effectively looks like the ground state is living in twice as many potential wells despite having the same characteristic impedance, which is provided by the linear circuit. And here I've just chosen a sort of random intermediate flux value of pi/3. So there's no degeneracy or anything.
Excuse me, is this factor of 2 twice more wells something very robust? Because it seems like if I turned off the tunneling, it would just be all in one well, or the wave function would be strictly localized, right? If in the limit.
It's not exactly a factor from this at this level. It's not exactly a factor of 2 because of the EC is changing correspondingly. So it's actually the envelope of this is getting slightly narrower as we increase this, but it's still so
you're doing something. You can do. The claim is more like you can do something to EC so that you can guarantee that it's twice more delocalized.
Well, in this case, it's just not exactly twice. It's more delocalized. It goes from say 3 to 5, but it's not 3 to 6. It's
Thank you. Sorry.
Yeah. No, it's a great question. It's a bit of a detail. I think getting from 3 to 5 wells is a fairly significant thing. But indeed, I think the important thing here is actually that although phi has changed, this is 2 pi instead of 4 pi. The actual sort of dimensionless figure of merit is how many wells are you actually in. Because I think when I say this, we're imagining introducing creation and annihilation operators A and A dagger, where the prefactor in the cosine in front of A and A plus A dagger is actually enhanced when you increase mu. And this is from the perspective of bosonic codes or something, the thing that's really important in designing other experiments. So to do this sort of generalized Josephson element, in the case of mu equals 2, what we introduced is this this kite element, and it's here in green. It's a loop formed by two identical Josephson junctions and 2 superinductances, and those have energies EJ and epsilon L. And this was sort of this was entirely born out of these earlier papers stemming from 2001 about the rhombus, which sort of there was a significant experimental paper in 2009 demonstrating roughly ground state delocalization using an array of rhombi. And for those of you who don't know, the rhombus is actually just the same loop, the same green loop, but if these 2 inductors were replaced by these same junctions. So it's a loop formed of 4 identical Josephson junctions connected on the 2 opposing nodes. And here, though, we specifically changed those 2 junctions in the rhombus to superinductors, or just inductors, in order to shunt the offset charge noise on these 2 intermediate islands. Okay, and then we basically arranged it in a standard fluxonium type circuit. We have a shunt inductance EL, and there's also, due to the connection leads, always going to be some additional capacitor epsilon C, which is something that is purely geometric in our case. It's not due to any junction. Okay, so there are 2 external fluxes in this circuit. There's one phi external, which roughly corresponds to the standard fluxonium-like external flux, and there's another internal theta external magnetic flux that biases this kite. So to understand a bit how this works, we can talk about the 2 most important degrees of freedom. Since it's so symmetric, we're inclined to introduce sum and difference coordinates. So phi sigma and phi delta. And here I'm plotting cuts of the potential energy landscape at the 2 extremal points of the external flux of the kite. So theta external equal to 0 and theta external equal to pi. And what I'm highlighting in dots is the lowest potential wells. So if we're interested mostly in the low energy physics, we should first of all look at where the lowest potential wells are, and then to see sort of the tunneling dynamics between them in a sort of a tight binding approach. So at 0 flux or theta external equals 0, there are basically just 2 low potential wells, and a fairly simple analysis of the tunneling between one to the other shows you that the most likely tunneling path is going to be this sort of 2-legged degenerate structure. At half flux, however, there are 4 lowest wells, and to get between any one, you also have to take this sort of diagonal path. but we're already starting to see the sort of physics that we want, which is more low-lying potential wells. Here, the fact that you have two degenerate ridges that are sort of interlocking here in this egg carton-like potential landscape is just due to the fact that we have two arms of the circuit. So physically, I think it's fairly clear to sort of to explain where these extra wells come from. Basically, at half flux, what happens is that the single Cooper pair tunneling in either arm of the circuit destructively interferes across the element. And this is actually pretty intimately related to the indistinguishability of Cooper pairs. So we really think about this kite as allowing pairs of Cooper pairs to tunnel, which is how it was designed. And that then maps back onto the cosine of or generalized Josephson element that I was showing before. Okay, so I'm going to take a few words about the theory here. This circuit has 3 degrees of freedom. There's phi sigma, phi delta, and also this total capital phi or different phi. And it's a 3-mode circuit, but it's and so it's not terribly complicated, but nonetheless it's a bit hard to make sense of. So here we're going to try to simplify it down to 2 modes. And to do that, we first make the main assumption, which is that this epsilon c is the largest energy scale in the problem. Experimentally, this was difficult for us to achieve, but nonetheless, the theory works still quite well, even when this is not so gigantic. So in this situation where we have 3 modes and the frequencies of the modes are roughly stratified, which is to say that we have 1 higher frequency mode phi and then 2 lower frequency modes phi sigma and phi delta, it's appropriate to use this sort of Born-Oppenheimer approximation where the procedure is to first fix the 2 lower frequency or nuclear sort of degrees of freedom at their classical values and treat them as parameters in the Hamiltonian for the remaining high frequency or electronic degree of freedom. So in this case, this is very simple. The electronic degree of freedom becomes a harmonic oscillator whose equilibrium position is set by phi sigma. And then the idea is just to freeze the electronic degree of freedom in its ground state, which depends on generally the other parameters, the nuclear parameters, and then to restore those nuclear degrees of freedom to their full quantum operators. So if we do that in this case, we end up with a 2 degree of freedom circuit, which is basically, in this case, you would have gotten the same result if you just minimized naively the potential with respect to phi. But here, crucially, this is quite different than if you had just taken phi to be 0 or something, because the inductive energy of the phi sigma mode has changed substantially. Okay, so we now have this 2 degree of freedom Hamiltonian, which is in terms of phi sigma and phi delta. And here we have the coupling due to the Josephson junctions. I'll remind you again what the potential energy landscapes look like. And here we're going to focus on specifically the case of pi. And in this case, in either case, actually, we can do a first intermediate step, which I'm not showing due to space, but we can introduce a 2D type bonding model where we have a countable index along phi delta and one along phi sigma. And then we can introduce a hopping amplitude between the various minima. In the particular case of half flux or theta external pi, we can actually we can do further and go straight down to a 1D type bonding model, where here I've introduced an index S, which is along the sites along this zigzag or gutter of low-lying potential wells. And we could have extended this much further. So not using just four sites, you can make this pretty far. So here, the inductive energy or curvature along the horizontal axis is given by the same as the phi sigma axis, which is this parallel combination, or sorry, it's a series combination of EL and then the 2 epsilon L's. So the important thing here is that the minima are separated actually by pi and not 2 pi as we walk along this zigzag path. And we also have the same phi external, which is determining the equilibrium position.
Excuse me?
Yes.
So the rate gamma that one that you're showing here, is it so it seems like it comes from some WKB approximation. So do you expect this to actually be exactly this or vary a little bit with extra tunneling?
Nothing's exact.
Okay.
There are many errors along the way. The Born-Oppenheimer will be one source of error. The second is going to the 2D type bonding. And then there's a third going to 1D type binding. And then a fourth using actually the gamma being this from this WKB approximation, which is strictly only valid when EJ is much bigger than EC.
Yeah.
So experimentally, our parameters are really on the edge of whether or not any of these things should work. But in general, we took this approach because it was the only path that we could actually solve it, or even attempt to solve it. So indeed, this gamma comes from a WKB or instanton type calculation for a single junction of Josephson energy EJ or and charging energy EC, which is the Josephson energy and charging energies for a single kite junction. And to see why this is the gamma that we should have chosen in going along this path, we just have to consider that a single rung of this ladder is going to correspond to a phase slip event in one of the two kite junctions, because it's at a 45-degree angle on the sigma delta plane. So for instance, this would be along the left and then along the right and then along the left again. So so then there's another source of error, which is that if you wanted to do a full instanton type calculation, you should invert this 2D potential and calculate the path of a particle starting at one hill and ending at the other. And this will be in general a curved path because you'll have a non-isotropic capacitance matrix. However, for a huge range of parameters, it's very nearly straight. So it's reasonably fair to replace it just by a straight line, in which case we can take this gamma, which has errors of its own. But nonetheless, yeah, sure. But yeah, nonetheless, we could call it quits at this type binding Hamiltonian, and actually, for the experts in the audience, this type binding model is the same as the quasi-charge representation. But we wanted specifically to actually recover a 1D continuous model, in which case what we did was we just found the only 1D Hamiltonian that also collapses to the same 1D type binding model. So in this case, we see that we have to have the inductive term in this 1D Hamiltonian has to match the same one here. And the fact that the minima are spaced apart by pi corresponds to this cosine 2 phi here. Also, if we look at the path between these adjacent minima, we see that the potential goes from minus EJ to plus EJ in the middle to minus EJ again, which means the amplitude of the cosine should be EJ. And then finally, knowing gamma forces us to choose this charging energy of EC over 4. So the 4s cancel. And I should say that really we're doing this really for two reasons. So the first reason is because a 1D continuous model is useful because we can introduce unambiguously a 0-point fluctuation amplitude of a phase and a charge in order to benchmark with an actual number, sort of the degree of ground state delocalization. But it's also useful in terms of designing bigger circuits, because when we make complicated circuits, it's very useful to use effective circuit elements with effective Hamiltonians. And in this case, we really want to think about the kite as being a Cooper pair tunneling element. And it's more than we want to. Generally speaking, the proof that the kite only allows pairs of Cooper pairs is much more robust than this sort of narrow path through type binding and Born-Oppenheimer. Really, if you can show that there should be a dominant cosine 2 phi term just by looking at the symmetries of the Hamiltonian. But here, in terms of to get actual energy scales, we have done this. We've taken this other route. Unfortunately, at zero flux, there's no single path through all of the relevant minima. Actually, you see this sort of looping structure, and that prohibits. We can write down a 2D type binding model, but not easily a 1D type binding model. So instead, what we do is we introduce a phenomenological Hamiltonian, which has the same inductive energy, but however, the minima we know are going to be spaced by 2 pi instead. So we remove the 2 And then we just add 2 fitted energy scales for the Josephson tunneling energy and the charging energy. So these will be eventually determined by a fit to the data. But the actual theory for recovering this is still a work in progress. It's proven to be difficult. Okay, so our experimental device is shown here. So what we have in this loop with the green outline is the kite loop. So you can see an inset of these small Josephson junctions here. They're about 200 by 200 nanometers. And then you also have these array junctions in the 4 quadrants of the kite loop. There are 25 junctions in each quadrant, so 100 junctions total in this kite. And then there's a shunt inductance shown in blue that has 50 junctions on the top and 50 on the bottom, so 100 junctions total. And then there is a small amount of shared inductance to an on-chip LC tuning fork kind of looking readout resonator. The array junctions are something like about 1.2 microns by 300 nanometers. And we have 3 control lines here. So there's a reflective or capacitive sort of coupling pin to probe the readout resonator. We also have 2 on-chip flux lines with bias T's, so we can actually route RF drives in as well. So
what's the ratio to the area of the junctions in the kite?
The ratio of the area is...
Yeah, are the array junctions large compared to the ones in the kite? And
yeah, it's about a factor of 8 experimentally. We could have pushed this a little bit larger. I can say that when designing this, we really wanted to have the array junctions as small as possible in order to maximize the inductance. But the cost of this is that the phase slip rate goes down. Or goes up, sorry. So in general, these arrays are quite slippery, but there is a substantial area difference, and of course the corrections are going to be exponential.
Thank you.
So,
yeah. And also talking about areas, the object is rather large. The loop areas are rather large. That's to keep the capacitance under control. Or
it was mostly actually just because we wanted to see many periods of oscillation. To test sort of the hygiene of whether or not this thing was going to be behaving periodically in both fluxes. We kept these lines very thin. That was mostly to decrease the capacitance. We connected these symmetrically so that there was the same amount of stray inductance in both arms of the circuit. Mm-hmm. In future generations, we really imagine decreasing this horizontal width substantially, at least by a factor of 5, maybe 10. But indeed, for comparing this to standard fluxonium or flux qubit devices, these are gigantic areas. So I'll just emphasize right now, this was never designed to be a protected qubit, and we were really just looking to see the Hamiltonian properties actually. So indeed, we expected, and flux noise is an issue if this is what you're getting at. But
yeah, okay, thank you.
Yeah. So basically, yeah, it's got 4 modes. There's 3 modes for the circuit and 1 mode for the readout. There are 2 flux lines and 1 RF drive. So it's not the most complicated circuit ever, but it's getting there. All right. So the first thing we measured is the external flux dependence, and so I'll say a few words about the flux lines. We have this IY, which is the vertical one, and IX, which is the horizontal one. When we put a current in, a DC current, it'll split symmetrically in both paths. And then generally a current in IX will induce a flux in both phi external and theta external because of some crosstalk, and the same goes for IY. So we don't expect that IX will directly couple to phi external, but it should be dominant due to just proximity. So our readout resonator is at about 5.6 gigahertz, and what we can do is just using a VNA, we can monitor the reflected phase at 5.6 gigahertz, which is sometimes the frequency of this readout, and that as we change these external fluxes by ramping these 2 magnetic field currents, the energy levels of the circuit periodically repel the readout resonance, and shift it up and down. And then we see, and it passes through the probe frequency of 5.6 gigahertz, and we see a sort of two-dimensional pattern looking like this. So here, the horizontal axis is Ix and Iy. We see these sort of butterfly type features, which are periodically repeating. And what you can see is that in addition to the periodicity, there are 4 different points of inversion symmetry. And from the Hamiltonian, we also expect there to be 4 different points where the Hamiltonian is even, so where the spectrum is expected to be inversion symmetric. So these will correspond to theta external and phi external being 0 or pi. Additionally, since we expect that Ix is going to mostly couple to theta external and Iy will mostly couple to, Ix will mostly couple to phi external and Iy to theta external, we expect that the more horizontal line will be for phi external, it's difficult, and the more horizontal one will be theta external. So you can see here the sort of skew and scale of the rectified axes. So here we're restricting ourselves. So here you can see the sort of primitive plaquette in flux. Here we're interested in biasing the kite at the 2 points theta external of 0 and theta external of pi, which are shown here in the 2 blue lines. And actually the width of the blue lines is corresponding exactly to the data that's being taken in the bottom panels and later in the talk. What you see is that here I'm showing the readout resonant spectroscopy as a function of the rectified phi external axis at the 2 different bias points of the kite. So you see a sort of typical anti-crossing type behavior for this LC oscillator, and it's a different one at the 2 points. Okay, so I'm just going to take a second to try to explain. Can I ask if these videos work in Teams?
They do for me.
It's smooth?
Yes.
Okay.
Perfect.
Yeah. So here I'm just plotting the potential energy landscape of a fluxonium qubit at 2 different phi ZPF values. So phi ZPF is related to this ratio EC over EL with a 4th root. That was the x-axis in the Mendeleev plot earlier, and this is the traditional amplitude that appears in the cosine in front of those A and A dagger terms. So for a moderate or a sort of high but standard fluxonium value of 2 for phi ZPF, we have multiple potential wells, but the ground state is mostly localized in the bottom one. And as I change the external flux, it just transitions smoothly to tracking the lowest potential energy well, except at the particular point of pi, where you get a bonding and anti-bonding type configuration. But the most important thing is that if you look at the energy levels, well, not the most important thing, but an important thing is that if you look at the energy levels for the ground and excited state, and specifically the difference, you see that it changes pretty dramatically as a function of flux, which is to say that there's a significant flux dispersion when we have this moderate value of phi ZPF. As a phi ZPF increases to 4, which is the Blochnium regime, and we see that at 0 flux we have the ground and excited state wave functions living in multiple wells, and we do the exact same thing. What happens is that the ground and excited state, since they're so delocalized between multiple wells, you get this sort of surfing-like behavior, and actually the raw energy levels themselves don't change as a function of flux at all. So in this particular experiment, we can really connect the flux dispersion of the first excited state transition with the amplitude of the 0-point fluctuations of the phase, and also with the ground state delocalization. So these are all really sort of signatures of the exact same physics here.
So, sorry, so the fact that the energy levels don't change, are not so sensitive to the external flux, is basically a signature of the function being, the wave function being so delocalized that basically, or is this a direct consequence of the delocalization?
In this particular case, in this particular circuit, in this device, yeah. It is. You can imagine, of course, there are circuits that have no flux dispersion but no delocalization as well. Like a transmon has no external flux, so it has 0 flux dispersion.
Yeah. Okay.
You could also imagine a circuit where instead of taking the limit for large phi ZPF, you could also have just made EJ very small, in which case there's a very small flux dispersion. But in this case, for us, since EJ is the largest energy scale in the circuit, measuring a small flux dispersion is really a direct indicator of a large phi CPF
I guess it's the equivalent of saying that the transmon has a large, has no charge dispersion, but it has a large.
So then it's probably an
exponential
suppression of the energy level dispersion as you go to the transmon limit.
Yeah, that's right. I think we should really think about blocknium as the dual to the transmon, where the flux dispersion is exponentially suppressed as it like the charge dispersion in the transmon.
Yeah, so these basically turn into Mathieu functions at the end. So, yeah, thank you.
Yes, absolutely. And if you really want to see this directly, you could introduce the quasi-charge representation as the direct analogy. Yes, so we measured this device, and in circles are the measured energy level transitions at both two of the external flux bias points at theta equals 0 and at theta equals pi. Here we've done this for the same plot or same range as in the previous plot where we see multiple oscillations. You see we've measured up to 6.6 gigahertz. The dominant feature is that the ground excited state transition has a much suppressed flux dispersion when the kite is at half flux versus when the kite is at 0. And here the flux dispersion at 0 flux is about 1.6 gigahertz, and at half flux it's about 140 megahertz. And this is a direct indicator of this two Cooper pair tunneling type physics that we expect in the kite. So I've also plotted in solid lines the fit to the full 3-mode Hamiltonian, which is numerically diagonalized. And here there are 4 fit parameters, which is EJ, EC, EL, and epsilon L. The epsilon C, that stray capacitance, is totally fixed from finite element simulations. So it's 12 energy transitions over 7 gigahertz, and it's all captured by this fairly simple 3-mode model. The other really interesting feature here is that actually at 0 flux, the overall spectrum is 2 pi periodic, which you can most obviously see in the lowest energies, the lowest transition. Some of these higher transitions have the sort of accidental feature of being almost pi periodic. This is due mostly just to the fact that there are 2 arms in the circuit, so there is some 2 Cooper pair tunneling physics even at 0, but it's only in the higher energy states. At half flux, however, all of the energy levels are very nearly pi periodic, with the minor exception that due to residual asymmetry in the 2 arms of the circuit, you have a small deviation at pi. I'll just remind you that the readout resonant frequency is 5.6 gigahertz, which corresponds to some of the gaps in the data here, and specifically the repulsion of the purple state and deviation from theory. There are 2 other transitions in light blue and light green, which are not visible experimentally. And this corresponds, we think we understand this, at 0 flux, these phi sigma and phi delta modes approximately decouple. And due to our inductive coupling scheme, only the energy levels that roughly correspond to the phi sigma mode will have any dispersive shift to the readout resonator. So here I've just pulled apart the energy levels which are mostly phi delta excitations. And so that's the blue and the green. You can see that the light blue is a mirror in terms of shape as the dark blue, but just with a higher frequency. So if you were to change theta external just a little bit, you would see these lines appear slowly, or? Yes, that's right. And actually, very close to anti-crossings, we can see the line, but it rapidly vanishes. Mm-hmm. So I could have maybe put a point here, but. And something that's very significant is that in this particular limit, although the flux dispersion of the GE transition is small, the flux dispersion of the higher transitions is getting bigger, much like in the transmon. So in this particular case, it's really very important that we measure the higher energy levels, because it really shows us that we are unambiguously in the case where this flux dispersion is not being suppressed from some parasitic effect. It's actually being suppressed because of ground state delocalization, which is in our case from 2 Cooper pair tunneling.
I have a question.
Yes.
But maybe this was a. So this is the 3-mode Hamiltonian that you're fitting, right? And have you tried to fit low energies lines for like, let's say, the effective tight binding Hamiltonian? Like,
yeah. So I can maybe say that here actually. So
perfect.
in the bottom panel. So okay, the 2 outermost columns are the 1D effective models. So on the right in panel F, there's actually no fit parameters. So this is the 1D spectrum, which is obtained through all the tight binding and the final continuous 1D model with the cosine 2 phi. So no fit parameters. Everything is just from the fitted values for the 3-mode Hamiltonian, and that gives us a phi ZBF of about 4. We do have those 2 phenomenological EJ tilde and EC tilde fit parameters for the 0 flux case, because the theory through tight binding was not tractable there. And here we find a phi ZBF of about 2. And so the agreement is quite good, actually. So it seems that at least for the lowest energy transitions, we can really get away with this tight binding trick. And it's a bit surprising that it's a bit surprising how good it is, because first of all, our EJ over EC ratio is not gigantic. And secondly, our epsilon C, this sort of stray capacitor, is pretty substantial. But nonetheless, up to about 4 gigahertz or so, the agreement is good, especially for the ground excited state transition. And with these 2 1D models, we can also plot again the wave functions, and we see that in the 0 flux case, it's really sort of fluxonium-like and living in 1 lowest potential well, but at half flux, we have this Blochnium, more like ground state delocalization, where we have it pretty obviously living in 3 wells. And the external flux values here are just pi over 3 again. Okay, so just to finish.
Sorry, can I ask another quick question? Just to understand well, so should I understand? So you said that in the higher energy spectra, there are multiple Cooper pairs tunneling at the same time, and this is basically, you can see this at the basically if you do like a Fourier transform of the function of flux, external flux, you see, I mean, the more periodicity, the more wells, the more Cooper pair tunnels. That's kind of an interesting picture to have.
Yeah, I would say that's about it. I think in this case, seeing a periodicity, I'm not sure actually how to do this mathematically, but if we could take a Fourier transform of all of the total spectrum, we would find that there's a sharper peak, a very sharp peak at pi periodicity, whereas here you can see that there would be a much bigger peak at 2 pi. This also has a residual small peak at pi, which is, I believe, due to the symmetry of the circuit. But
I see. Okay. I see. So if we follow this, like at the high lines, there would be even something at pi over 2, right? A peak at pi over 2. If we look at the very
yeah, for instance. Yes.
Yeah. Okay. Thanks.
Yeah, this dark green one I think is actually showing like a pi over 2 almost type periodicity.
Thank you.
So okay, so a couple words about this actual parameters we measured. First thing is the asymmetry model we use for this circuit is the simplest one we could imagine, which is to say that the 2 small junctions have slightly different areas. And just doing statistics on test junctions for this device, we know that these things will usually differ by about 5%. And actually what we find by just tuning this parameter by hand until the spectrum matches after performing the fit, we find about a 6% difference in the areas. We have an EJ, which is about EC, which is about 6 gigahertz. And that corresponds to a standard junction plasma frequency of about 17 gigahertz. And our shunt inductance is about 200 megahertz, and the internal superinductance for the kite is about twice as big. And this makes sense because, as I mentioned, there are 100 junctions forming EL, and forming epsilon L, there's 50 junctions. And they're all the same area. So the interesting thing is that the epsilon C are this sort of stray or parasitic capacitance due to just connection leads, which are indeed far away, but still non-negligible, so 2.5 gigahertz. And this is not a fit parameter. This is just determined by H of SS. So there are 4 external flux sweet spots, which is to say there's sweet spots in both of the 2 phi external and theta external knobs at 0, 0, pi 0, and so on. I'm just restating the measured GE transition frequencies at those 4 places. We measured the dispersive shifts to the readout resonator. They are generally very big. They're tens of megahertz. This is due to the amount of shared inductance that we used, which was so large because we were interested in seeing all the higher transitions. Our T1s measured range from about 5 to 40 microseconds, and they follow the exact same curve as the frequencies. So the highest T1 is the lowest frequency, and this aligns very closely with a dielectric loss model, which is consistent with other experiments in the group. For T2, we measured Ramsey and echo. The T2 Ramseys are constant at about 500 nanoseconds. The T2 echoes are about 4 times bigger. And as we said, the loop areas are gigantic, so we expect that T2 Ramsey might be limited by flux noise. In this case, it has to be to second order because these are double sweet spots. But nonetheless, second order flux noise with such a gigantic loop area, just a simple calculation with a standard spectral density gives you exactly these numbers. So additionally, though, we can also try to measure T2 on the slope, which is to say not at these sweet spots, and we find that it's unmeasurably low. So I would say that these T2 Ramseys are exactly limited by flux noise, which is also consistent with the enhancement in when adding a single echo pulse. And a factor of 4 is very typical for flux noise. One other factor is that I mentioned these junctions in these superinductances are very slippery. So phase slips occurring across the array junctions can, in principle, encircle a fluctuating offset charge. And so this can also be a source of dephasing. Although at this point, it seems like the only direct evidence we have is for flux noise. So that's basically it. I think our main conclusion is just that we have observed a pretty unambiguous signature of ground state delocalization. And it's a circuit that uses only conventionally fabricated Josephson junctions, but sort of more complicated circuit quantization type engineering. Our next plans are first to actually do a experiment which was inspired by Gerhard Kirchmeier's paper in Nature from 2013, where he measured the Q function for a Kerr cavity. And here what he sees is the top panel is experiment and the bottom panel is theory. What he sees is collapses and revival of the upper initial prepared coherent state. And we want to do a similar experiment, but with this type of kite connected to an oscillator, where the small junction energies of the kite are very small, so that the kite overall has a perturbative effect on the oscillator. But we expect to see, instead of this diffusive type evolution of a coherent state, we expect to see tunneling type evolution. So we think this is intrinsically linked to sort of a non-local type oscillator Hamiltonian. But down the road, we're interested also in connecting a kite with a facelip element as a way to potentially realize GKP codes in a Hamiltonian way. But this is a bit more distant. So thanks.
Okay, thanks a lot. Really exciting. So we had already some questions during the talk, but other questions? So please raise your hand or another. Good. So Alex, you have a question? So yeah, you can go ahead.
So you showed us a table of the various experimental parameters exactly. So I'm wondering if you, if I recall correctly, the diagram you couple through a shared inductance, right, to the readout resonator. So have you actually used your formalism to compute the cross-curve?
Yes.
And does it agree with what do you have good agreement between your
yes, I have
before and this experimental data?
Yeah, it's about right up to about 50%. I didn't measure dispersive shifts at all the various flux points, which would be required to really fit that coupling. But here, because the shared inductance of this LC mode is actually half of the total inductance, there are 3 junctions, and 7. So with such a turns ratio, you really expect gigantic highs, which is, I mean, something I almost don't even have to do a simulation for. Because also one thing that's really one thing that's cool about this device is that we can think of these 2 flux points as being just 2 different fluxonium Hamiltonians, or this being fluxonium and this being Blochnium. And in such a case, we expect the sort of usual things we know for fluxonium to work also at these 2 particular bias points, one being that the chi is biggest at half flux, which is very close to what we see.
I see.
But I hear it's big everywhere, but indeed.
Okay. I have a question myself. So why, I guess, so why did you choose inductive readout? It was not to lower the EC, or like not?
Yeah, so I can say the reason why we did inductive readout. So usually if you do usually if you do okay, so it's mostly not to load the ECs of these small junctions, or also this epsilon C between these. Any coupling capacitor to some other mode would inevitably do that. And I think if you're pushing for large phi ZPF, you want to basically maximize EC. So adding extra coupling capacitors, we would load all of these capacitors. From a more practical point of view, I have done this before, so it was familiar.
Okay. Okay. I see. And okay, another question. I have one also. How do you? Okay, so now you have mu is equal to 2. So so I read your thesis a little bit, and I know that. I mean, that makes sense. Like you can build by adding branches and loops. You can like build a larger interferometer of Cooper pair, and go to cos 3 theta, cos 4 theta.
Yep.
But then I guess you won't be at the sweet spot anymore, because you need to flux bias at some weird values for flux.
Yes. Well, so I have a couple answers to this. Indeed, what you're saying is that if you want, you can add more arms to this kite circuit, where each arm is a junction and an inductor, and we could add a 3rd arm, in which case the bias point would be 2 pi over 3 in both loops. We'll get a 4th, and it'd be 2 pi over 4, and so on. The brute force way is to add more flux control lines, and there's nothing really experimentally stopping us from adding 20 of these.
Right.
But if you wanted to be a bit more elegant, you would want to really balance nicely the areas of all of these different loops within the extended kite, and then you would eventually possibly be limited by the residual loop area difference. And sort of B field inhomogeneities. So this is kind of ongoing work. But I don't personally. I personally see the adding more flux control lines is not terribly difficult. But here it was pretty easy for us to use 2. Yes.
I see. But this I mean the flux noise. I mean if your bias your loop at 2 pi over 3, like you because here you show the flux dispersion along phi, right? But along theta, you have also some flux dispersion.
Yes. So along theta. So if I plotted the other axis here, you mean?
Yeah. So here
Yes.
at theta equals 0 and theta equals pi, these are sweet spots. Right.
Those are sweet spots, but indeed, so one thing I forgot to mention, which is important, is indeed there's always a flux dispersion in theta. So if you this point to this point, you can see that it's changed. So indeed, at the 4 sweet spots there, and if you want to calculate the flux noise susceptibility, you also need the second derivative with respect to theta. In which case, at the 4 sweet spots, this is about the same number, which is why we expect theoretically that the T2 Ramseys, if limited by second order flux noise, is going to be about the same number, despite the fact that the sensitivity is clearly much higher at theta external to 0 than at pi.
Okay.
So this is something that's not shown in the plot. But
Okay.
I might have another question, maybe. So can I?
yes.
Of course.
So it's this is related to the degeneracy. So if we look at the potential energy landscape at pi flux, there's this 4-fold degeneracy, which allows you to write down this kind of tunneling Hamiltonian. So I'm wondering how sensitive this 4-fold degeneracy is to the external flux. So if does local flux noise break the degeneracy, or is there some kind of exponential protection?
So I'm not sure exactly what you mean by local flux noise. Here, the 4 wells that you're talking about are what's shown in the movie, basically.
Okay.
So they're not exactly degenerate, but they're the 4 lowest wells. And you can see they're all relevant to actually model where the ground state is going to be.
Okay, I think you answered my question. Yeah, that's great. Thank you. So this is the zigzag, but unfolded.
Yes, exactly.
Okay.
This is just basically along the zigzag.
Okay, thank you.
Okay.
So
Well, I think
maybe I will have a question.
Okay.
Joaquin.
Go ahead, Agustin. Yeah.
Okay. Yeah. So my question is just practical. Is it possible to reduce EJ a little bit to maybe help even further the localization of the wave functions, or there is a limit, let's say, on how small this EJ can be?
That's a good question. We could reduce it a little bit more. We basically here I can say that we use these cross-style junctions as a way to really well control the area of these small junctions, and we could have gone further. So we went to about 6 gigahertz, but we were trying to balance basically how low we could reduce EJ, which would also increase EC given the same plasma frequency. But also we wanted to make sure that the 2 junctions were not too asymmetric. So generally the problem is that as you make much smaller junctions, there is more noise in the area. So it would have been a bigger problem for us to have 3 gigahertz junctions that were 20% different than 6 gigahertz junctions that were 5% different. But I think that this is actually like I don't think this is a very hard limit. You can imagine doing other types of junctions. First of all, you can imagine evaporating multi-layered oxide, just to increase the thickness of the junction, the oxide. You can also imagine doing things like nanowire junctions or granular aluminum junctions, where the insulating layer is actually extended instead of just being a thin oxide.
That's great. Thanks a lot for the answer. I understand.
Sorry, we have a next another question from Alex, right?
So can we think of the states that you're showing as being single fluxon states? If we think of a single fluxon excitation that is allowed to, these 2 on the right.
So here I would say that
the blue on the right.
The blue one here is a single fluxon. The green one is close to the other fluxon. Whereas here I think you can only really describe the ground and excited states in terms of multiple fluxon states, where this would be, say, -1, 0, +1, +2, or something.
Got it. Yeah.
Yeah, I think let's say the superposition amongst multiple fluxon states is exactly the same thing when I'm saying the ground state is delocalized. You can't really get away with a single fluxon type description.
Makes sense. Yeah, thank you.
And just if you're thinking about the language of the excited state transitions, basically if it looks like a zigzag, then you have a fluxon-like behavior. Whereas if it's looking like a sort of washed out flat type transition, then you have yeah, exactly. Which is, it's not exactly plasmons because they look more like grid states than they do like Fock states. So for those of you that are interested in sort of GKP type language, this is one reason why we're interested in this type of circuit, because this is starting to resemble grid states.
Thank you.
Sure.
Okay, so if there is no other questions, let's thank Clarke again. And yes, thanks a lot, Clarke.